You're watching a Channel 98 NBISD TV production.
From the dark, cold, lonely basement of the central offices at NBISD, I'm Kevin Corpy, and this is That Geometry Show. Today is Lesson 22, and we're going to be talking about three-dimensional objects. Not two-dimensional, three-dimensional, so we're kicking it up a dimension here. We're going to be talking about all different types of three-dimensional figures. We're going to be looking at prisms and pyramids and polyhedra. Sounds pretty interesting, right? So download those worksheets from the website, www.newbraunfels.txed.net, and play along with me right there at home. And we'll get started. All right, Lesson 22, this is going to go along with your Geometry Chapter 11.1, 3D Figures and Polyhedra. So we are going to be exploring three-dimensional shapes today. And three-dimensional shapes, the dimensions we're going to be looking at are things that have length and width, which all 2D objects do, like this sheet of paper. But now we're going to add the third dimension, depth. So we're going to be rising up out of the page here. Now, in Euclidean geometry, which is, remember, planar or two-dimensional geometry, it's very difficult to depict a three-dimensional drawing on a two-dimensional sheet of paper. And so we have some clever artistic ways to do that. And one of the ways is by looking at what's called a perspective drawing. And a perspective drawing gives the illusion of three dimensions on a two-dimensional sheet of paper. And there's actually a couple ways that we can do these perspective drawings. The first way is called a corner view. And if you look right here, there's three examples of what a corner view looks like. It's basically a shape that is drawn kind of at an angle. And it is on two dimensions, but with this nice shading right here to give it that three-dimensional look, it creates the illusion of three dimensions. Now, whenever you're given a corner drawing, you need to be able to orient yourself around the drawing. We say that this piece here, as we're staring at the object from this direction, is the front of the object. Okay? So I'll draw the arrow pointing at the front, and it's at the angle, because we're staring head on at the corner. So this would be the right-hand side. I'll put an R for right. If we imagine walking around the other side, the back side here that we can't see, it would be the left, and the nice shaded green portion would be the top, and of course it's sitting on the bottom or the base. Now, I know this might sound a little strange, but whenever you're trying to imagine a three-dimensional object, it's kind of helpful and sometimes kind of fun, too, to imagine that you've shrunk down and you're actually walking around this object on the page, that you're staring at it from all the different sides. Sounds corny, sounds cheesy, but it really does help you visualize what's going on. So the corner view is one way that we can do it. Another useful way is to look at multiple views of the solid in two-dimensional format, but we're going to need more than one drawing. And it's usually given as the top view, the left view, the front view, and the right view. So this would be an example. Now notice in these drawings right here, there appears to be a darker line on the top and the front view. That darker line is to give the illusion of a shadow line. It usually means that there's a cliff or something there that is creating a darker line. So let's look how we can use these multiple dimensions of 2D drawings that represent a solid. Which of the following corner views represents the above solid? Well, let's go ahead and start with the front view, since that's the way that I told you to orient yourself with the corner views. If we notice the front view, imagine staring. We're on the ground level, and we're staring straight on at one of these diagrams. What we're going to see is, first of all, a wall that's a block of 4. It's going to be 2 wide by 2 high, and there's going to be a visual cliff here, or some type of shadow line that's going to denote some type of change. Well, let's come down here to our diagrams. And again, I'm going to draw the arrow that points to the front of each of these. It's helpful to orient ourselves. Well, if I notice on C and B, when I'm staring at this blank, boring wall. I'm not going to really see any visual line on it. So chances are, just by looking at that single view, those are not going to be the answers. Now look at choice A and D. Those are the two that are left. If I look at choice A, staring head on, notice there's two tiers here. We have a lower level and an upper level. So these are going to create lines. But notice this is also a single cube. This is not extended all the way across the width. So I would see a shadow line staring straight on that would look something like this, staring straight on. Because it's that going to be all the way across? No, it's going to drop straight down. So A is probably not the answer, which means D is probably going to be it. Again, if I'm staring straight on, notice this little cliff goes all the way across the width. And so this line right here, when we're on the ground level facing it, is what we see here. And so just with a single view, we can actually conclusively determine that D is the right answer. But let's go ahead and look at a couple of other views just to make sure. This is the right view, which means if we're standing on the right-hand side, facing it this way, is this in fact what we see? So we're imagining that we're standing right here on the ground, and we're staring at the wall. We're going to see this backwards L looking thing, and if you look right here, that's exactly what this is. So it's drawn at an angle, it's perspective drawing. And the left side view would be the L shape. So if we imagine walking all the way around, doo-dee-doo-dee-doo-dee-doo, and we're staring at it from this side, you can imagine that we would see that same L shape. And just to be thorough here, the top view, we're like in a helicopter and we're staring straight down on it, okay? Are we going to see this? Well, we approach it from the top, and we come up and we look straight down, and now this is the visual line that we're seeing. But it looks like the same as the front view. So takes a little bit of practice. It's kind of strange and unfamiliar, but with a little bit of practice, you can get good at these. You just kind of have to shape your brain so that you know what you're looking at. Now, in that example, we were given multiple representations, two-dimensional drawings, and we matched it up to a corner graph. Now what we're going to do is we're going to be given the corner view, and we're going to try and match it up with it appears to be the right-hand sides and the left-hand sides of the two-dimensional depiction. So notice this image here. It looks like just a bunch of diamonds connected together. But you've all seen those puzzles like you're in the mall at those little kiosks and you have to stare at them for a while and you see something that's not there. Kind of the same thing here. If you imagine approaching it from this side, you can begin to see the layers. There's going to be a layer right here and it's going to go up. So I'm going to have basically a staircase right here, up one level, up another level, and there's going to be this wall that's up against one side. Okay, so you can add shading if you need to. Now, I'm looking for the right and left sides, not the front side. So if I walk up to the right-hand side, let's see what I'm going to look at. I'm going to be looking at this, which is a backwards L. Okay, so which of these from the right-hand side is going to be the first one has a backwards L? This one has the dark shadow lines for a backwards L, and this one does as well. The other two do not, so it can't be A and it can't be D. Now notice what else am I going to see beyond this little step. I'm going to see a block that's going to be 1, 2, 3 high by 2 wide. So if we look at B, it's going to be 3 high and 2 wide. And there's no other visual cliff here. And notice on part C, there's a darkened line right here, which would kind of give the impression that there's another layer going on here. So it's not going to be choice C, it's going to be choice B. Now, if you were inconclusive just from the right-hand side, of course, walk around, take a look at the left-hand side. And this one's a little difficult to see. You have to imagine standing behind this wall, and what are you staring at? Well, because you can assume this wall goes all the way down, you're staring at just a big old blank wall that's 3 high and 2 wide. And that would be the left side view. Well, the one we chose, notice if we look at it, there's no darkened line. This is just a blank wall that's 3 high and 2 wide. The other answer choice has a little darkened area here, which again kind of gives the impression that there's something missing or a void there. So we have basically 2 cues that choice B is correct. Okay? Pretty easy once you get the hang of it. How do you get the hang of it? You work a lot of examples. All right, now all the surfaces in these solids we've been looking at have been flat. And we call those flat surfaces, we call them faces. So now we're talking about the anatomy of these solids. The flat surfaces are called faces, and solids that have flat surfaces that enclose a single region are called polyhedrons. That's one way. Or you can actually call it polyhedra. Polyhedra. And they're both plural. This is the one that's more commonly used, but you might see both of them in your textbook. All the faces of polyhedra are polygons. We looked at those from a previous episode. And the line segments that connect them are the edges. All right? They're edges. And they intersect at vertices, or each edge intersects at singular a vertex. So we have polyhedra made up of flat faces that are polygons. The edges run along the sides where the 2 faces meet, and the edges join each other at a vertex. Here's a diagram to help you see what I'm talking about. We have a simple polyhedra here that is actually a cube, and it's made up of flat faces. So the face right here is a polygon, and in this case our polygon is a square. And right here where the two faces meet are the edges. So you can actually outline the edges. So that's where the two faces meet. And each of the edges are joined at these points called vertices, which is plural, or a vertex, which is singular. So faces, edges, and vertices, that's the anatomy of polyhedra. Now, just like there's special polygons, there's going to be special polyhedra, of course. And the first type that we're going to look at, one of two types, is a prism. Now, if you've done any experiments in a science class where you've refracted the light into its primary colors, you probably did it with a prism. A prism has a very specific mathematical definition, and here's what it is. We have two congruent faces. Congruent faces, remember, means the polygons making up the faces have corresponding sides that are the same length and corresponding angles, and we do call those the bases. And the polygons that are the bases are in parallel planes. Okay, so if you think of your hands as being parallel planes, they're flat. So they're either right on top of each other or they're side by side. And then we connect those two bases that are in parallel planes with some more polygons, and we call those the lateral faces. Now, lateral means side, so these are the faces that wrap around the side. Now, we classify these prisms by their bases. We classify, I'll write this out, we classify by the bases. So if we look at this one here, this is a prism. We have a rectangular base in red, and on the bottom we have another rectangular base, and notice these two are parallel to each other. They won't intersect like this. No, no. Now we wrap it around with 1, 2, 3, 4 other faces around the sides. Those are the lateral faces. So we call this a rectangular prism. Some people might call it a brick or a piece of a 2x4. Okay, but it's really a rectangular prism. Let's go to this one here. We have two bases, and they don't have to be top and bottom. They can be side to side. I have two triangular bases that are parallel like this. So they're triangular. And then we have one on the front, one on the bottom, one on the back enclosing it. This would be a triangular prism or a cheese wedge. It's always fun to try and name these shapes. Makes math a little more fun. Over here we have what looks like maybe a hat box, anyone? All right. But we've got another prism because we have a hexagon on top, which is one of the bases, a hexagon on the bottom, which is parallel, and then we have 6 faces wrapped around the sides, so those are the lateral faces. And because the bases are hexagons, it's a hexagonal prism, not a hexagonal. The accent's on the A. Hexagonal. Ooh, hexagonal prism. There you go. The other type of special polyhedra we're going to be looking at are the ones that you're probably familiar with if you've ever studied ancient Egypt or watched a show on the History Channel, and those are the pyramids. Okay, a pyramid is a special polyhedra or polyhedron that has all faces except one. All faces except one intersecting at a point. The one that doesn't intersect at a point is called the base. And again, we classify pyramids by the base. So if we look at this diagram here, we call this one a triangular pyramid. So the colors show the different lateral faces here. But if I connected the lines from here to here, we would have a base that is triangular. So this would have 3 lateral faces that intersect at the top, or the vertex, and the base is triangular. Now the ones that are in ancient Egypt, that the ancient Egyptians built, are this type. They're square pyramids. And we talked about this on the very first show, how they built these things with the Egyptian rope stretchers, and they've got these square pyramids wrapped around several square foot on the bottom, and they're all accurate within to remarkable accuracy for the technology of the day. But we basically have a square base, and we have 4 faces that are made up of triangles. So it's a square pyramid. And then we have a pentagonal pyramid. We can have basically any pyramid we want so long as we can construct it. So in this case, we have a pentagon for the base, and this would have the 5 lateral surfaces all connecting at the top. So pyramids are pretty cool. Now, polyhedra, beyond that, can also be similar to what polygons were, and that is regular. We had regular polygons, which meant all the sides and all the angles were congruent. Well, we can have regular polyhedra as well. And what a regular polyhedron is basically if all the faces, not some of them, not just the top, not just the bottom, but if all the faces are composed of congruent polygons, all the faces, the lateral and the bases, have to be congruent. Well, this would also imply that all the edges are the same length. Now, it has been proven mathematically that are only 5 such regular convex polyhedra, in case you were wondering. There's only 5. Okay? And because the ancient Greeks knew about them, and in fact, this guy right here, Plato, had written about them extensively in his journals, sometimes these 5 regular polyhedra are sometimes called the Platonic solids. The Platonic solids named after Plato. So here he is. Maybe he's saying in this picture, solid! Perhaps. I don't know. I wasn't there. Now here they are. We have basically 1, 2, 3, 4, 5. That's all there is. So we have this one here, which is called a tetrahedron. It has 4 faces, and this is composed of 4 equilateral triangles. All the sides are the same. We have a hexahedron, which is basically a cube. It's composed of 6 squares. Square is a polygon, all sides congruent. Then we have an 8-face called an octahedron, a 12-face dodecahedron, which kind of looks like a soccer ball. And if you're wondering if it is a soccer ball, in fact, it's not. A soccer ball has a pentagon for a face, but it's joined by hexagons. So a soccer ball is made up of pentagons and hexagons. So although it looks like a soccer ball, it's actually not. And I don't know if Plato actually played soccer, but that's irrelevant. Now we have a 20-face icosahedron. And notice that this not only has 20 faces, but they're also composed of equilateral triangles. So of the 5, we actually have 1, 2, 3 of them that are composed of equilateral triangles. But that's it. No more, no less. Okay? Now, an interesting tidbit here, a guy named Leonhard Euler, the most prolific mathematician of all time. He has written more about math than anybody. He actually did one of the proofs. There's several proofs that there's only 5. But he came up with the interesting fact that if you have any of these 5 regular polyhedra, the number of faces, F, minus the number of edges, E, plus the number of vertices, V, always equals the magical number 2. Now we can verify that for these. Let's look at the tetrahedron. It has 4 faces, so that's 4, minus, we can count the edges, 1, 2, 3, 4, 5, 6, so 4 minus 6. And then it has how many vertices? 1, 2, 3, 4. So if I add 4, I get 4 plus 4 is 8. 8 minus 6, that equals 2. And if you have time, you can go ahead and verify that for all the others. But this was actually a pretty remarkable discovery. And once he proved that this had to be the case, you can jump off from here and prove that there's no other combinations that give you the number 2. Okay? All right, it's time for a break. But before we go, I just want to tell you a little apocryphal story about that last guy we were talking about, Leonhard Euler. He was one of the most prolific mathematicians, after all, and he went blind in one eye after several years of working. And get this, they asked him how he was going to continue doing his math after he went blind in one eye. A funny guy, not only brilliant, pretty funny. He said, well, now I shall be less distracted. I don't know. What an optimist. Think about that while we go to these public service announcements.
There comes a point in your life when you realize you're not a kid anymore. Suddenly, you have to make decisions. You have to make choices every day. This is the time when you define yourself, or you let others define you. You quickly learn that there are 2 ways to go: under the influence or above the influence. I am above the influence.
All right, I can't even do this during the break, so I don't know how he went the rest of his life producing valuable, meaningful mathematics with only one eye. But anyway, he did it. Anyway, let's get right back to the geometry show. Now, it gets really interesting when we take all these polyhedra and we begin to slice them. And there's several ways to slice things. When we slice with a plane, okay, you can imagine your hand being a slicing plane, and it intersects a solid parallel to the base, or the bases, we get a cross-section. Now, cross-section is one of those terms that can be used a little more loosely to just interpret slicing along any plane. But mathematically, we're going to stick to slicing parallel to the base. Now, cross-sections, they're useful. They allow us to analyze a sample of a 3-dimensional figure in a 2-dimensional environment, much like our 2-dimensional depictions of solids did earlier. And they'll usually take on the shape of the base itself. Let's look at an example. Which of the following is a cross-section of this figure? It's a familiar figure. It's a set of stairs. Okay? Well, this down here is the base. So if I'm slicing this way. I'm slicing straight across this way. So if I slice, it's going to slice like this. Okay, we're going to basically cut that in half. What would the cross section look like? Would it look like this, or this, or this, or this? Well, because we're slicing it parallel to the base, it's going to basically have the shape of the base, which is going to be the shape of the top. So slicing it, we're going to get something that looks like this, and then we'll have the little step in there. Now, if this is the front, and we're staring down, it's going to look like this. Okay, so that would be the answer. Now, slicing along different planes, we can achieve a lot of different, very useful shapes, which brings us to my favorite part of the program called the Say What? All right, here we go. We're going to be slicing up a cone. Now, question out there to you is a cone a polyhedra? The answer is no, it's not a polyhedra. And the reason is because, remember, polyhedra have to have flat faces. And a cone kind of has a round shape around here. But it is very nice, and there's some nice applications when you slice it up. You can slice a cone with a plane. Imagine your hand chopping here. You can chop straight across, which is our definition of the cross section, parallel to the base. You can slice at an angle and come out the other side. You can slice at a steeper angle and come out the bottom. Or you can slice perpendicular to the base, which would be here. Now, if you go on to take Algebra 2 or Pre-Cal again, you'll be studying these things. These are called conic sections because they come from slicing or cross sections of a cone. And the applications of the cross sections of the cone were studied in ancient Greece by people like Apollonius and Hypatia. They had a profound influence on what we use in the modern world today. So let's take a look at each of these a little more carefully. I have a cone here. It's a wooden cone. And the cross sections are outlined in different colors. So if I take this cone and I slice it like this, parallel to the base, I'm going to get this slice right here, which is a circle. Okay? Circles have applications. If I take this and I slice it at an angle that's slightly slanted, I get this right here. And this is what's called an ellipse. Okay? That's the proper mathematical name for an oval. If I slice it at an angle again, this way, I get something that looks like the gateway arch, but it's actually not. It's a parabola, and a parabola has many, many uses. And then if I slice it perpendicular to the base, right here, I get this, which usually we talk about if we have two cones, and we get something that looks like a parabola, but it's called a hyperbola. So let's look at an application of each of these, and you'll be amazed that you've have so many of these things around your house. All right, the circle. I don't think I have to tell you how useful a circle is, right? Not only does it have, it's the shape with the greatest rotational inertia, but it also makes for a pretty smooth ride when we're driving down the road, right? It becomes the basis of our transportation system. Wheels, wheels, everywhere we have wheels. Circular gears, okay? CD players, electric saws. You can look around anywhere and you'll find circles in action. It's a cross-section of a cone. Now the ellipses. Ellipses are like circles that have been sat upon, and they're kind of flattened out. They have many different shapes and sizes. They can be long and skinny, or they can be almost round. That's called the eccentricity. Well, ellipses have very, very important applications. Here's some of them. Orbits of the planets around the sun follow elliptical paths, as well do the satellites like the moon, and some of the comets like Halley's Comet follow elliptical orbits. Now here's a diagram of what an elliptical orbit is. An ellipse has two special points inside that are not the center, called foci or foci. Each one is called a focus. The sun, in this case the sun will be blue, is at one of the foci, and the planet travels around the sun in this orbit. This right here is called the perihelion. It's when the planet is closest, perihelion, to the sun. And over here, this is the aphelion. And Kepler did a lot of work with this, and Newton helped him describe the equations. But the interesting thing about ellipses is that the sun is at one foci, and it's generally considered that there's nothing at the other foci, but it might be interesting to look into that. Another interesting application of the ellipse is its reflective properties. If I look at these two foci, anything that's emitted from one foci will travel and bounce, reflect off the perimeter of the ellipse, and it will always travel right back to the other foci. This property is evident if you've ever been to the U.S. State Capitol. They have a room called the Whispering Room, and it's an ellipsoidal room. And you could stand at one point in the room, and someone can stand at the other point of the room, and even though there's a lot of noise in between, you can whisper something very secretive, and it'll bounce off the wall and go right to the ears of the other person. Also, if anyone you know has ever had kidney stones, there is a medical procedure called lithotripsy. And lithotripsy is basically using the elliptical properties, the reflective properties. They sit you in a vat, and they have a frequency transmitter at one foci, and they position the other person in the water at the other foci, and the transmitter emits sound waves, which any sound wave alone is not going to be enough to break up the stone. But because they're all traveling off the wall, and they're all hitting the foci at the same time, the concentration of the sound waves is enough to very passively break up the stone. It's a pretty cool non-invasive procedure. And it uses the cross-section of a cone. The parabola, parabolas are everywhere. It's basically the path of any object thrown in the air, like a football. It's the effect of gravity. If you've ever taken a drink out of a water fountain, the water fountain looks like that. That's a parabola. Engineers use it in suspension bridges as the curve is kind of tethered down. But they also have very nice reflective properties. Most of y'all have cable or satellite. If you have cable, you're watching the show. Great. But some of y'all have satellite dishes, and you may be watching this on DVD, available at the school library. But the satellite dishes that are hanging on the side of a house are basically parabolic receivers. And inside you have the transmitter, which is set at a point called the foci. And here's the property. Any incoming signal that is coming in at parallel rays will bounce off the parabola, and it will concentrate into the focus. And that's how you get a concentrated signal. So this little receiver right here has to be calibrated so that it's exactly at the correct position so that your signal comes in nice and strong, so you can watch the football game or that geometry show if it came on satellite. Now, if you look at this in reverse, the headlights in your automobile work in the reverse fashion. They actually have a bulb at the foci which shines the light, which is not very bright. But as it bounces off the reflective wall inside the headlamp, it'll shoot out a very strong beam, parallel beam, that will amplify the signal of the light alone. And finally, the hyperbola. The hyperbola has many useful applications in navigation. You might have seen navigational maps that have a bunch of hyperbolas drawn on, and the system is called LORAN, which stands for Long Range Navigation. It's based on the time difference principle. If you're out here at sea and you're at this point here, you can have two receivers on a stationary bases on land that transmit a signal back and forth to you. And what's true about hyperbolas is the distance one, I'll call this D1, the distance from where you are to the first receiver, and the other receiver, D2, that distance, D2 minus D1, actually the absolute value of it, is always the same number. And it doesn't matter where you are. So they can use that to help locate you. And this was primarily used before GPS, but still it's used today. Very important principle. And again, it's nothing more than the cross-section of a cone. Okay, unfortunately we're all out of time again today. I know it goes by so quickly. Time flies when you're having fun, right? But at least next time you're out on the soccer field kicking a soccer ball around, you'll be thinking, hey, soccer ball, not a polyhedra, which means you'll be thinking about math. Or maybe you won't be thinking about math. I don't know. Anyway, until next time, I'm Kevin Corpy, and I'll catch you on the flip side.